Okay, so welcome back to IIT Bombay Virtual Commutative Algebra Seminar. This week we have two lectures by Professor Manoj Kummini from Chennai Math Institute. They are about big Cohen-Macaulay algebras. So today he will speak on applications, and on Friday he will continue with the theory of big Cohen-Macaulay algebras. So Manoj, please, you may start your lecture.
Thank you. Thank you, Jugal, for this opportunity to talk in the seminar series. And so I will talk, give this lecture and the next one on big Cohen-Macaulay algebras. Today, this is part one, and here we will look at some of the applications, relatively classical applications of big Cohen-Macaulay algebras. And the slides are already online, so that's the issue. So these lectures are just some exposition on the big Cohen-Macaulay algebras conjecture of Hochster and its proof in the prime characteristic case. And so, as I said earlier, in this lecture we will look at the conjecture and some applications. And in the next lecture, we will look at a proof by Huneke and Lubesnik in the prime characteristic case. So here's roughly what I plan to do. We'll just quickly look at the background, where these conjectures came. Then we will look at absolute integral closure, a specific property called weak functoriality, and then we'll briefly look at, so the absolute integral closure discussion will be in prime characteristic and what would happen in characteristic 0. So we will look at that. And then we will look at some applications. And the key application that we would look at is this vanishing of maps of tau. And we will see two corollaries of this, which is that pure subrings of regular rings are Cohen-Macaulay. So for these two topics, I will briefly sketch how the proof goes. Then there is another important application called the direct Saman conjecture, which I will not discuss the proof or how to go from vanishing of tau to that statement. Then we will look at another application different from coming from these homological conjectures to tight closure, and I'll conclude with just a brief statement about so everything that we discussed till now would be on equicharacteristic and what is new, what is known now in the mixed characteristic case. I shouldn't say what is known now, just some. Okay, so here is just a copy of from a note from notes of Hochster. So this is about the background is homological conjectures of Hochster, and the old reference for that is the CBMS notes of Hochster called Topics in the Homological Theory of Noetherian Rings. And so this is the picture that I've drawn now, that I've taken now, is from the second reference, the current state of the homological conjectures. Let me just slightly zoom that in. So what we would look at is this diamond here that I have marked in red. So the top here is this conjecture called there exist weakly functorial big Cohen-Macaulay algebras. Okay, so that's what we would like to understand. And that implies this vanishing conjecture for maps of tau. We will define these things, or at least state the theorems as we go along. So this is this vanishing conjecture of maps of tau, and then we will look at these two corollaries of this, which is the direct summons of. We will look at this, and we will just mention this in passing. So the diamond is written like this, but on the other hand, if you look at the right side of the diamond, it is just weakening of the conjecture. Here it is. We'll define what we mean by weakly functorial, but the first arrow here is just removing that weakly functorial. And then here it says we don't care about algebra, just a module is enough. And then independently on this direction also one can prove the direct Saman conjecture from this direction. But but we will not discuss this side of the diamond, but it's the left side as we see that I would like to at least give some discussion. Yeah. So throughout this talk, R denotes a Noetherian ring, but not necessarily, so R algebras are not necessarily Noetherian. In fact, most of the R algebra that we will consider will not be Noetherian, okay, or may not be Noetherian. So definition, let R be a local ring. So underlying assumption is that when I write R, I mean a Noetherian ring. Okay. Let R be a local ring, and an R algebra S is said to be Cohen-Macaulay, a Cohen-Macaulay R algebra, if a system of parameters of R is an S regular sequence. So in the usual sense, if you take a system of parameters, then it does not generate the unit ideal in S, and successively they form non-zero divisors as you go modulo more and more elements in the sequence. And often when we discuss this, we will refer to things as big Cohen-Macaulay R algebra. It is just to emphasize that the algebras and modules are not necessarily finitely generated. It is just this condition. A system of parameters of R is an S regular sequence without insisting that the object that we're looking at is finitely generated as an R module. So it is just a way to remind us, it's not really the part of the definition. And one more definition now. If R is a local ring and S is a Cohen-Macaulay R algebra in the sense above, then say that S is a balanced Cohen-Macaulay R algebra if every system of parameters of R is an S regular sequence. Okay. So this is what we mean by balanced. So just to go back to this picture, so this is from this reference 2 that I've written here. In that, when Hochster writes Cohen-Macaulay algebra, he means balanced, and so he doesn't state it explicitly at every stage. So in this context, one should read. I mean, the way we have defined it, one should read the main conjecture here as there exists weakly functorial balanced big Cohen-Macaulay algebra. Balanced is implicit in that picture. Okay, so that's the definition. Now let R be a domain. The absolute integral closure, which we denote by R plus of R, is the integral closure of R in an algebraic closure of its fraction field. So now we state two theorems. So the first is by Hochster and Unike. Let R be an excellent local domain of positive prime characteristic. Then R plus is a balanced, okay, and I put in brackets big to emphasize that we are not requiring or even hoping to get that it is finitely generated. Okay? So R plus is a balanced big Cohen-Macaulay R algebra. Okay? And another version, I mean a similar theorem by Unike and Lubesnik. Let R be a local domain of prime characteristic that is a homomorphic image of a Gorenstein local ring. Okay. So one can guess that the proof is going to use some local duality here, which it will. And it is this theorem that we will discuss in the next lecture, its proof. Okay. And then R plus is a same conclusion. R plus is a balanced bigger Cohen-Macaulay algebra. And so the hypotheses for these two theorems are not comparable to each other, but they have a large intersection. Many rings are both excellent and also homomorphic image of Gorenstein local ring, at least if one completes. Okay, so there is some huge overlap in the hypothesis of this theorem, but they are not, neither implies the other, the way that it's written here. Okay. So this is, as I said, it is this theorem here that we will discuss a proof in the next lecture. Okay, so now we come to the idea of weak functoriality. So if R2S is a local map of excellent local domains, or local domains that are homomorphic images of Gorenstein rings. So the hypothesis on R and S should be that it satisfies the hypothesis of one of those theorems above of prime characteristic. Then so throughout these notes, when I say characteristic P greater than 0, I mean prime characteristic P. Most of the time I work only, I make statements only for domains, so it's probably okay. But even if I didn't explicitly state it, I do mean a prime characteristic. So then there exists a commutative diagram, such as this. okay, where R to S is the given map, and R to R plus and S to S plus are the maps to the absolute integral closure. And here there is a map from, the point is that there is a map from R plus to S plus such that the diagram commutes. So this is what is meant by weak functoriality. So how do we prove the statement? Okay, so first of all, notice that a map from R to S will factor as some quotient of R. So if you call this map phi, this is R modulo kernel of phi, and injects into this. So if we want to prove this, we can split this picture into two, in which there's a surjection. So now we will replace S by this image and call that R to S surjection, and then followed by an injection. So we'll replace this by R and call that as an injection. So if you can understand these two cases, if you can prove that such diagrams exist for injective maps and surjective maps, then one can put them together and prove it in general. Okay, so let's try to sort of see the proof of the statement. So as I said, this is what is called a weak functoriality. Okay, that given any map, there is a map in the big Cohen-Macaulay algebras that we constructed. Okay, so let's do the injective case first. Okay, that's a little easier to see. So here is the picture, and we can as well assume that this R is a subring of S, and this denotes an algebraic closure of L. Okay. L is the fraction field of S, and this is the algebraic closure of L. And we may as well assume that calculations are happening inside L bar, and all rings that we consider are subrings of L bar. Okay, so R is inside S, and S sits inside S plus, which sits inside L bar, and then one can just check that there is an algebraic closure of K sitting inside L bar, and elements of K bar that are algebraic over R will be a subset of S plus, will be a subring of S plus, and this is the map that we have. So given an inclusion, we get a map from R plus to S plus. So this is the sort of. Now we consider a surjective case. So in order to understand what happens in the surjective case, one needs a characterization of absolute integral closure. Okay, so for a domain, an Euclidean domain A, the ring A plus is characterized by the following three properties. Okay, it is a unique ring satisfying these three conditions. One, A plus is a domain, so and contains A as a subring. A plus is integral over A, and every monic polynomial with coefficients in A plus splits into monic linear factors over A plus. And this is not very difficult to check. Okay, so A plus is characterized by A plus is a ring. Any ring satisfying these three conditions will be isomorphic to A plus, will be isomorphic to an absolute integral closure of A over A. Okay. So now let's apply this, because we would like to understand in this case what is S plus. Okay. So write S as R mod P, where P is a prime. Okay. And let Q in R plus be a prime lying over P. This is an R to R plus is an integral extension. So there is a Q lying over P. And then one can check that R mod P plus. So this thing here satisfies one, two, three, 4S. Okay. I mean, if you put S, it satisfies these three conditions. So that would say that S plus is isomorphic to R mod P plus, and therefore there is a sorry, that's not what I meant to say. I typed. Sorry, clearly that's not what I meant to say. What I meant is R plus mod Q. Sorry, not this. One has to check that this ring satisfies. Sorry, that ring satisfies the conditions for S plus, and therefore this is an absolute integer closure for S. Okay? And therefore it is a quotient of R plus, which is what we wanted to prove. I mean, we wanted a map from R plus to this S plus. This is the map. Okay. Yeah. So now we'll come to characteristic 0. So this above results do not hold verbatim in characteristic 0 in dimensions greater than or equal to 3. And why is that? So we'll just look at an example in dimension 3, and this explains the problem. So let's consider a normal local domain containing the rationals, three-dimensional, and XYZ is a system of parameters. Okay, let's take an A that multiplies Z into the ideal generated by XY. So this is just saying A is in R, AZ is in the ideal generated by X and Y in R. Okay. So whether there is an A satisfying this property which is not already there, which is not in XY, tests whether R is Cohen-Macaulay or not. Okay. So it's easy to check that it also satisfies, it multiplies Z into XY, the ideal generated by X and Y inside R plus. Okay. So this is easy to check. Now, suppose that A is in this ideal, XY R plus. Okay. Then we can write A as S1X plus S2Y for some S1 and S2 in R plus. Okay. Now, there will be some finite extension S containing S1 and S2. These are integral over R. S1 and S2 are integral over R. And so there in some finite extension one can find these things. Okay. And let's take fraction fields to be K and L, K for R and L for S. It's a finite extension. Now, because we are in characteristic 0, there's a non-trivial trace map, K-linear map from L to K. And if you just apply a trace map to this expression, okay, what happens is A gets multiplied by the degree of that extension. So there exists a non-zero integer M. And because R contains the rationals, it's invertible. Okay, such that the trace of A is some, because A belongs to R, trace of A is just some M times A. And on the right side, when we evaluate trace is K linear and hence also R linear. X will come out, Y will come out, and we would get something like this. We'll get an expression that's inside the R ideal generated by X and Y. So in other words, this would say that A is also in the ideal generated by X and Y. And therefore, the conclusion is that the system of parameters X, Y, Z cannot be R plus regular unless R itself is Cohen-Macaulay. Okay, so just going to the absolute integer closure will not get us a Cohen-Macaulay algebra unless the base ring itself is Cohen-Macaulay. So this is what happens in characteristic 0. This is what happens for absolute integer closure in characteristic 0. Okay, so, but nonetheless, there is a, there is a positive result, which is the following. And this again, so this is a paper of Oxter and Unike. Anyway, these references are there at the end. Okay, which is the one that discusses infinite integral extensions and big Cohen-Macaulay algebras. Okay, so if you have an equicharacteristic local domain, Rm, then there exists a local, but not necessarily an Noetherian ring, Sn, with a local map R to S, such that S is a balanced big Cohen-Macaulay R algebra. Okay, so so let's see what the. So in characteristic P, this is just what we have stated earlier. If characteristic is positive, then we consider R is local, so complete it, and then go modulo prime P, which is a prime of maximal dimension. so that every system of parameters of R is also a system of parameters of R hat and also a system of parameters for R hat mod P. And this is now an excellent domain of characteristic, of prime characteristic. So it has an absolute integer closure. So take that, call that thing S. Okay. The only question now is that here there is an assertion that there is a local ring. Okay. Why is S local? So this Arindam also touched upon in his lecture last week, that since R hat mod P is complete, S is local. So absolute integer closure of a complete local domain is also local. Okay. So S is local. So that's why S is local, and the map sequence of maps here is local. I mean, the maximal ideal sits inside the maximal ideal in S. Okay. So in prime characteristic, I mean, this theorem is not, except for this observation, this theorem is not substantially new. This is just building on what was stated earlier. But in characteristic 0, this requires work, and that uses Artin approximation and reduction to prime characteristic. And then one proves that there's an appropriate big Cohen-Macaulay algebra in characteristic 0 also. Okay. So characteristic 0 requires more work to finish. Okay. But it goes by reduction to characteristic P. So, yeah, so, sorry, okay. So this is the vanishing of maps of Tor. So let me, so this I will sketch a proof, assuming the existence of big Cohen-Macaulay algebras. Okay. And from this, I will also sketch a proof of the fact that direct summands of regular rings are Cohen-Macaulay. So here is a statement. R to S to T equicharacteristic Noetherian rings, okay, with R and T regular. So the first and the last are regular. The first one is a regular domain. S is a module finite extension of R and torsion free over R. Okay. Then for every R module M and for every I greater than or equal to 1, there is a natural map which comes from the map S to T. From Tor I MS to Tor I MT, this map is 0. Okay. So in this proof, I will, for proving or sketching a proof of this, I will follow the Case CBMS notes called Tight Closure and Applications. Okay. Yeah. So, so if the map is non-zero, then it would remain non-zero after we localize T appropriately. Okay. So something in the support of the image, if you localize there, it would still be non-zero. And then we can complete, that's a faithfully flat map, so it will still remain non-zero. Okay. So we can replace T by a complete local, regular local ring for a suitable prime ideal Q of T. Okay. So hence T is a complete regular local ring. So this is one reduction. Now every module, these are R modules. Every R module is a direct limit of its finitely generated submodules. So using that, if you can prove that the map of Tor vanishes for all finitely generated R modules, it would also imply for all finitely generated modules. Okay. So we'll also assume that M is finitely generated. Now we'll localize, so T is now a local ring. Okay. It has a maximal ideal, contract it to RS and localize and complete at that prime. Okay. So now R and T are complete regular local rings, and S is some module finite ring lying module finite ring over R, torsion free also. Okay, now let's look at the map from S to T. Its kernel is a prime ideal of S. So it contains a minimal prime ideal P of S. And P, when we contract P to R, it would be 0. That's because S is torsion free. Okay? There's nothing in S that's killed by any non-zero element of R. Okay, so we get this. So now let's so the map is S2. So we have a map S2 T factors as this, and this gives a map in Tor like this. Okay, so to prove that map, we want to show that this is 0. Okay, it's enough to prove that this map is 0. This map is 0, and therefore we can replace S by S mod P and assume that S is a complete local domain. Okay, so this is okay. So now here is the setup that we have. Okay, R is a complete regular local ring. T is also a complete regular local ring. Okay, and we have already proved the existence of weakly functorial balanced big Cohen-Macaulay algebras. Okay, so that's A and B. A is a balanced big Cohen-Macaulay algebra for S, and B is a balanced big Cohen-Macaulay algebra for T. And weak functoriality ensures that this thing commutes. The four terms here commute, and R maps like this. So this is what this is the picture that we have. Okay. So now R to S is finite, and therefore A is a balanced big Cohen-Macaulay algebra for R also. So A is balanced big Cohen-Macaulay algebra for both S and for R, and B is for T. So now we need a fact about big Cohen-Macaulay algebras over regular local rings. So this is so this again, I didn't mention this in the last lecture, but I think towards the end of this lecture he mentioned that two properties are equivalent. Okay, so here is what we have. Since R is a regular local ring, an array algebra C is a balanced big Cohen-Macaulay algebra if and only if C is faithfully flat over R. Okay? So this it's not very difficult. Okay? So one needs this fact, this characterization of big Cohen-Macaulay algebras over regular local rings. Okay? So hence A is faithfully flat over R and B is faithfully flat over T. Okay, so this is this is what we have. So now let's consider the maps and Tor that we would get. Okay, so just looking at the diagram. So just go back. It's just S to T, S to A to B. This four terms S T A B. Okay, apply Tor. Okay, so now for all I greater than or equal to 1, okay, we get a commutative diagram of Tor modules, Tor I ms to Tor I ma, Tor I ms to Tor I mt, and like this. Okay. So now, because A is faithfully flat over R, this Tor is 0. That's so therefore this diagonal map is 0. So this is the first observation that we want to make. Sorry, this is 0. Yeah, sorry, because I'm overlaying the slides. If I write something, it disappears after. Okay, I'll mark this after I'm done through this overlays. So okay, now so the claim is that because B is faithfully flat over T, the right vertical map is injective. Okay? So let's quickly look at why that is the case. Okay. First of all, this is the module here, Tor MT, and then this is Tor MT tensored with B tensored over T. This is injective. This is because T to B is faithfully flat. Okay. So we will see this a little later. This is a property about purity of the morphism, And one example of a pure ring map is faithfully flat ring map. So this is what. Okay, so this is the first observation. Okay, so I'm explaining why the right vertical map is injective. Now, we want to identify this. We want to say that this thing here and this here are the same. So let's take a free resolution of M over R. Now we compute two things. Okay, so if you take F tensor over R with T and take its homology, and then take the homology and tensor the homology with B, because T to B is faithfully flat, one can put this thing inside here. One can put this thing inside here, and so we would get this isomorphism, and non-zero also, faithfully flat. And the left side here is just tor empty, this module that we have. Okay? And on the right side here is this. So therefore, this map is injective. Yeah. So therefore, this vertical map is injective. So our conclusion is that because the module here is 0, the diagonal map is 0, and this vertical map is injective. Therefore, this horizontal map must be 0, which is what we wanted to prove. Okay, that's the that's a sketch, modulo the reductions that we did earlier in the proof, reducing to local case, reducing regular local case. This is what the key argument is. Modulo those reductions. Okay, so now, so we'll now look at some applications of vanishing tor. So the first thing is the statement that pure subrings of regular rings are Cohen-Macaulay. This theorem itself goes back much before, much before all of the other things, and due to so this goes back to the study of invariant rings of algebraic groups by Hochster and Roberts. Okay, so here is the definition: a ring map R to S is pure if the map from M to M tensor S over R is injective for every R module M. So one can check that faithfully flat maps are pure. So we use this in the proof in the sketch of the previous theorem. If we have a ring map, okay, if it splits, that is, there exists an R linear map S to R such that sigma phi is identity on R. Yeah, phi first and sigma, correct. Sigma phi is identity on R, then it is a pure map. The phi is pure. So sorry, when I said it here, I mean phi is pure. Okay, and converse holds if phi is finite. Okay, so here is a concrete example of a condition of the second statement. If you have a finite group and we a finite dimensional representation G over K, or a field K, such that the cardinality of G is invertible in K, then let's take S to be the symmetric algebra of the dual, meaning the functions from V to K, and R to be the invariant ring SG, then R to S splits. And this uses the existence of the Reynolds operator. Okay? And that requires the fact that one can divide by order of G, and this is what. So this 3 is a concrete example of 2. So the theorem, which I mentioned earlier, is that if you have a pure morphism of a few characteristic rings, and with the target regular, S is regular, then R is Cohen-Macaulay. Okay. This was the, this is the thing that proved that invariant rings for linear algebraic groups are Cohen-Macaulay. Hochster-Roberts theorem. So again, I'm only going to just briefly sketch what is. So maybe I think I'm going really fast. Are there any questions?
Nothing in the
Okay.
chat box as of now.
Okay. Yeah, I think I'm only like it's only 6:05 and I'm already like 50. Okay. So we again standard arguments. Well, okay, not so standard. One can reduce to the case that R is complete local, and one has to worry about. See, this is not a finite. This is not a module finite map. So when we reduce and complete, when we localize R and complete, what happens to S has to be checked. But one can reduce it, and one can still preserve the property that the morphism is pure. Okay? So this is,
Manoj,
yeah.
This question from Jugal.
Yeah.
What about infinite group case?
Yeah. So this is the I mean GLN, all of those things that is taken care of by in the Hawks-Roberts paper. This is true. I just gave an example for which one easy. I mean, one knows how to write the Reynolds operator and check that it is split. That's all.
Okay.
Yeah. It is true. I mean, this is the. I mean, that statement that rings of invariance of Cohen-Macaulay applies far more generality than the non-modular group, finite group action case. Is that okay? Is that huh?
Yeah, I suppose.
Okay. Yeah. Okay. Yeah. So one has to do a little bit of work to check that purity is preserved when we localize R and complete. Localize, it's a little easy to check, but completion some checking has to be done. These are done, for example, in the Hawks-Roberts paper. Okay, but now that R is a complete local ring, equicharacteristic, there is a complete local. This is a Cohen structure theorem. I mean, from the. I mean, there is a. R contains a complete regular local ring over which it is module finite. Okay, so this is just Cohen structure. And so let's take a regular system of parameters for A, okay, x1 through xb. And let's take M to be the quotient. Now, see what we want to prove, let's just go back. What we want to prove is that R is Cohen-Macaulay. So this is R is Cohen-Macaulay as a module over itself, okay? Which is to say that it's because of module finiteness, it is the same thing as saying R is Cohen-Macaulay as an A module, but R and A have the same dimension because of this thing, and therefore it's the same. So let me just write that here. R Cohen-Macaulay as R module, if and only if R Cohen-Macaulay as A module, which is to the same because they have the same dimension. So this is finiteness of the map A to R, and because they have the same dimension in this setup, it's the same thing as R is free A module. Okay, so this is what we are going to prove, that under this hypothesis, the vanishing of tau will imply that R is a free A module. Okay, so this is where we're going. Okay, so now let's consider this commutative diagram. This is. Oh, actually, I made a mistake. Okay. Sorry, which is why I said this is a sketch, and I forgot what the sketch was. So I'm assuming here that R2S splits. Sorry, I put the extra assumption that R2S splits, but one does not. I mean, this is the extra hypothesis, which I didn't state. Okay. Yeah. Sorry, I meant to add when I wrote here sketch. I meant to say we will further assume that it's a split morphism, but I forgot to write it. Okay, so this is the extra hypothesis. So now let's take tau. Oops. Okay. I'll write that thing again. So let's take tau. M is the residue field for A, so we get this thing, and S is regular. So we have completed R, we have localized and completed R, and S is still regular. Okay. So then, therefore, this map is 0. This map here is 0. And but this is, I mean, the identity map factors through 0, so which means now that tor R MR is 0 for every positive I, and that is the same thing as saying M is a free A module, and hence it's a Cohen-Macaulay A module. Since it's a Cohen-Macaulay R module, sorry, not M. R is a free A module, and so it's a Cohen-Macaulay ring. Okay. R is a Cohen-Macaulay ring. Sorry, I meant to write. I want to add this extra hypothesis that hypothesis is that R2S is not just pure, but it splits. Okay. So this is the sketch. So this again is a consequence of the vanishing of tor. Now, this I'm only just going to state the Dirac-Saman conjecture. And so the statement of the conjecture is this. If R2S is a module finite extension and the base is regular, then it's a Dirac-Saman of S as an R module. Okay. In other words, there is a map from S to R that splits this inclusion map. Okay. And one can again prove that the vanishing of the map of tor implies the Dirac-Saman conjecture. And the proof is a little longer than the proof of the previous statement, Dirac-Samans of regular local rings. So I avoid giving a sketch of this proof. Okay. Are there any questions now? So now I want to give another application. I mean, I want to leave this homological conjectures aside and discuss the application of big Cohen-Macaulay algebras to tight closure. So are there any questions now?
I don't see anything in the chat box.
Okay, so now this I mean I just state the definition here, but we have had enough talks in the series that I think by now everybody would have seen the definition of tight closure. But let me just state it here just for the sake of completeness. So I will write it only for domains that are be a domain of prime characteristic and I and R ideal. The tight closure of I is by definition the set Z.
Manoj?
Yeah.
Parangama is asking if you can go back to the last theorem.
This one.
No, the second last theorem.
This part. The statement.
Yeah.
Yeah.
Is this the one? Parangama, you can unmute and
yeah.
speak.
Where you use purity, if you use splits.
No. I know. I use something stronger than purity, which is why I said it's a sketch, because I forgot to write here that the sketch applies only for split morphisms and not pure morphisms.
Okay.
Yeah,
And
pure
one more,
morphisms, the proof, Hochster-Roberts proof goes by looking at certain maps in local cohomology, etc., which I think will take us a really long time.
so in general, when can you move from pure to splits?
No, meaning, so this is what we, sorry, let me just go back to the,
Means are there situations where you can go, generally you can go from pure to splits. Splits imply
no,
pure.
split is a stronger condition.
Yes.
But here is the thing, two here. If you have a ring map, if it splits, it's pure. I mean, that's just a stronger condition. If phi is finite, then these two conditions are the same.
Like co-kernel is the finite thing. I said the same.
No. When you say phi is finite, I meant as a morphism. I mean, S is so this means S is a module finite.
Oh, okay.
Module finite R algebra. Yeah, the morphism is finite. Okay, so if that happens, then these are same. Okay, so and I was just giving an example of that in 3 here, that this condition does does occur. That you have a finite map in which the map is split and hence pure.
Okay, and for that, in that statement, is a so you
Which
first
statement? Which statement?
in that
Here.
proof of that theorem
This
that
one.
we were talking about, the pure this one, yeah.
Yeah.
So the first statement, reduced to the case when S is regular and R is complete regular. Is this
Yeah.
the same way you did before that you localize it? What is the
No. This requires more work because see here you're local. There you're localizing and completing in the target ring.
yes.
Okay. Where one doesn't have to worry about. There's no priority to be preserved. But here that's not the case. Here, see, when you do this, you want to make sure that the map still remains pure.
Pure, yeah.
Although I sketched it, I further assumed then that it splits, but that's because I just want to shorten the proof and just give an idea how vanishing of torque comes in. But but here you're localizing at R, and you will invert corresponding elements inside S. That part is okay. But once you complete an R, R to S is not S is not a finitely generated R module. So there you have to complete with respect to the extended ideal. But then you have to check that it's still regular,
Yeah.
and that the morphism is still pure. And so there's
So
more
you
work.
will take as a product of those product of something. It will split as a product of something if you localize if you complete
S is
A
not
plus X.
S is not a finite R module, and we are not completing. Yeah. So R to S could be. Typically in the applications for linear algebraic groups, the fibers are positive dimensional, right? So you have to handle the. This is not a finite map, module finite map. So it need not split. It's not a finite module over a complete local ring.
Okay.
Yeah.
And the second thing you say Cohen factorization, that is Cohen factorization and Noether normalization, right? That is
You prove.
okay.
Yes. Yes.
Yeah.
In the
Okay,
general framework for Cohen structure theorems.
Okay.
Equicharacteristic. Yeah. Sorry. I'll fix these typos and I'll upload the slides after fixing these things. Okay, so this is the direct Saman conjecture. Sorry, I saw this. Okay, now we come to tight closure. The tight closure of I a priori is just the set. There exists a non-zero C such that for every integer E, C times Z to the P to the E is an, sorry, not this, I to the P to the E. Sorry, the Frobenius power. I will fix these typos when I update the slides. Okay. So this is what we have, and so then one can check that this is an ideal that contains. Right? And I'm not going to discuss. I will just say it has very nice properties and it is very useful. Beyond that, so it's worth. It's worth understanding how one can describe the tight closure of I, etc. Okay. So here is one observation that if S is a module finite extension of R, then if you extend I and contract it back to R, those elements are in the tight closure of I. Okay. So this is a property about contractions for module finite extensions. Okay. So this is so now. So now one asks the question, if you extend I to this largest integral extension, that is R plus, and then contract it to R, do we get I star, the tight closure of I? So this is not a completely random question. So there is a theorem of Hofstede, which is proved using this idea of what's called solid closure, that if R is a complete local domain of prime characteristics, and I is an R ideal, and X is an element of R, that X is in the tight closure if and only if there exists a balanced big Cohen-Macaulay R algebra S such that X is inside IS. With this condition, it's the same thing, X is inside B. So remember, this S might depend on X. But still, there is some, in order to check for individual element, one has a similar description. One can extend it to some large algebra and contract it, and if x is still there, if x takes this x is inside is, then it is inside I star. So there is a theorem which like this, and in the Hoxton-Uneke paper also there is some variation of this theorem which I was a little longer to state, so I didn't state it. But here is a positive answer to exactly that question. So let R be a locally excellent Noetherian domain of prime characteristic, and let x1 through xd be elements of R such that they form a part of a system of parameters in every localization of R that contain at a prime ideal containing x1 through xd. Okay. So one can just the most obvious simple case of this, one can just take R to be a local excellent domain, and then x1 through xd to be a full system of parameters. So just okay, and then write I to be the ideal generated by these elements. And if you extend I to R plus and contract it to R, we would get the tight closure. Okay. I won't discuss the proof, but the strategy of this proof goes by translating to local cohomology what it means for some Z to be inside IR plus to be on the left hand side of this, and for some Z to be on the right hand side. Okay. So the statements will be translated into local cohomology in terms. So notice. So I will just briefly say. I mean, this is not the whole proof. So there is a natural map from R mod I to the. So this is in the local case now. Okay. X1 through XD, full system of parameters. Okay. So once that happens, there is a map like this. Okay. And if you take a Z, which is not inside I, then it gives an element in the local cohomology, the top local cohomology module. So there is a map like this, okay. Top local cohomology module, and then some condition on the top local cohomology module, which resembles the type closure condition for ideals, and similarly this condition that it belongs to R plus, IR plus. So they are, I mean, so in Smith's proof that these Z belonging to the left hand side and belonging to the right hand side are translated into some conditions about local cohomology classes, and then there is a technical checking that those two conditions are the same. That's how this theorem is proved. So again, I will not sketch the proof any more than this. Okay, so now we'll come to the end of this talk. So what about mixed characteristic? So this is recent work, last five years or so. There exist weakly functorial big Cohen-Macaulay algebras in the mixed characteristic situation also. Okay. So earlier, all that we have discussed is just equicharacteristic.
Manoj,
yeah.
Parangama has a question.
Sure. Yeah.
Parangama, please.
In the last slide,
yeah.
in the statement x1 to xd is just a set of elements, right? But you said HDMR, the top local cohomology.
Yeah. But I'm saying the last that I've written in blue here applies only. System of parameters. It doesn't. Yeah. Okay. I mean, the proof goes to checking this.
Okay.
I mean, after all reductions, it comes to doing this for local rings and top local cohomology, where if you take a Z inside R, the image of Z inside R mod I gives an element local cohomology class, and whether Z is inside I star will be translated to statement about that local cohomology class. Similarly, Z is inside IR plus will be translated to a similar condition, and then one checks that these two conditions are the same. I mean, not that those statements are, those checkings are easy, but yeah. Okay. So yeah. So in the mixed characteristics, yeah. Go ahead.
In the previous situation, R plus will become balanced this algebra, right?
Yeah, it is balanced. Yeah.
But may not be finitely generated.
It is not finitely. No.
It is never finitely generated. Possibly.
No. In positive dimension, this is not finitely generated overall. I mean, finitely generated even as an algebra, not as a module. I mean, they're the same. It's an integral extension. They're the same, but it's not finitely generated.
So when you're showing that Z is in I R plus, are you considering HDM of R plus?
No, 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 no. The condition that Z is in IR plus will be translated into a statement about the class of Z. I mean, see, Z induces a class in the local cohomology module. It will be translated into a statement about that class.
Okay.
Okay. In HDMR itself.
Oh, in the HDMR.
Yeah, yeah.
Okay. Thank you.
Yeah. So, yeah. So there exists this thing, and so one can prove direct Saman conjecture. I mean, going back to the diamond that I started with, this is what's proving the top part of that diamond. So all the consequences follow, and more recently, I mean, these are also being used to study or define singularities in mixed characteristic. And I'll just mention names associated to, and without actually going to the results. Even stating those results are sometimes not easy. So so these are the work of these people and others. Okay. And so that's studying. Okay. And here's just a list of references. Most of the stuff that I did for today's talk either came from the top, the first reference here, or in any case, tight closure CBMS notes. And this is that result of Karen Smith. Okay. And yeah, yeah. So I'll stop here. Thank you. Are there questions now? Hello? Sorry.
Sorry. Thank you, Manoj. If anyone has any question, please unmute yourself and come forward and ask.
Yeah, so I have a question about the description of tight closure.
Yeah.
So
which page?
No, this was stated for system of parameters.
Yeah, this one.
Just 1 moment. Yeah, so it was stated for system parameters.
Yeah.
But what about other ideals?
Other ideals, I don't know. So there is a paper in the Hochster-Huneke paper. There is a result which talks about general ideal, but it's not the same statement. It's not saying IR plus contracted to R is I star. Sorry, I forgot the exact statement. It goes something like if X is in the closure of I extended to to R plus, or maybe any Cohen-Macaulay algebra, then it is in the tight closure or something. I'm sorry, I forgot the exact statement.
So left-hand side is always contained in the right.
Left-hand side is always contained in the right-hand side. The way if you phrase the question as this, left-hand side is always contained in the right-hand side. It is the containment that.
But the right-hand side may not.
Yeah, I don't know. More general than this, I do not know. What
Manoj, I have a question.
Yeah.
So what happens to this intersection in characteristic 0? This IR plus intersection R?
That would just be because it splits, right? The trace map says IR plus. If R is if you assume R normal, then the map from R to S in equicharacteristic 0. If you take a map from R to S, I mean S a module finite extension, then the I mean and an overring, not a quotient, but something inside S, R plus sort of thing. When you contract it back, you would just get the ideal itself because it splits. Right?
I see.
Yeah. The non-triviality of the trace will force it to split.
So it will be I itself.
It will be I itself. Yeah. You will not pick up anything bigger.
I think Kaushik sir had a question in chat box.
Okay.
Yeah, I just noticed. Thank you. Do you need S regular? Oh, this was asked sometime back.
Oh, I see. Which was the
It is
Kaushik is there?
same theorem I was asking about.
Yeah, yeah.
Yeah, in the statement about pure maps,
Um, sorry. Let me
instead
just
R2S is
I'll go back.
pure.
I'll go back. Yeah, yeah.
In that theorem, did you need S to be
Yeah,
regular?
because the vanishing of tau, vanishing of tau requires like this: A inside R inside S, where S and A are regular, and R is module finite over A, and torsion free, which is often the case because what we have done really is we started with some arbitrary R, we localized and completed, and then we took a Cohen, using Cohen structure theorem, we found an polynomial, power series subring. That's how we got the A. Okay, so yeah, S is regular is used because in this setup we want these two to be regular.
Manoj, sorry, I have one more question if you don't mind.
Yeah.
So in that question where S is a pure extension of R and
Yeah.
S is regular, then R is
Yeah.
Cohen-Macaulay.
Yeah.
What happens if S is just Gorenstein?
What happens
Is there any such
if
result?
Gorenstein? This is just Gorenstein. I don't know. I'll have to think. I don't know the answer. I mean, I don't know an example which might suggest it is false, or yeah, I don't know right now.
Okay, thank you.
Do we know any example of big Cohen-Macaulay algebras other than like balanced big Cohen-Macaulay algebras other than R class or about that class?
If you're asking whether I know, I don't. But
No,
maybe
is
it does
it
know.
known?
I don't know. I don't.
Okay.
I mean,
So the theory is developed just for
No. But
R
sorry,
class?
if you're saying if you're saying in characteristic P, I don't know. The mixed characteristic cases are all some extremely large algebras, which are not the A plus. I mean R plus. Okay. But I cannot describe them, so it's not.
but I
That's
think
why
in the equicharacteristic case, the existence was known, but it was not known that it is this explicit in characteristic P. In the equicharacteristic case, Hochster, didn't he prove that big Cohen-Macaulay algebra exists?
I mean, in the CBMS notes, he proves modules, which is enough for the direct command conjecture, not algebras.
Yeah, big
There's a thing that he calls some.
Right. He used to call them Big Macs.
Huh?
Right. Big
Oh,
Cohen-Macaulay module. Right, Big Macs. Right.
So he, so there he proves modules, not algebras. But that is enough for the direct command conjecture.
Right. This may be in his CBMS notes.
Yeah, it is. It's there in the CBMS notes.
Right. So this result that I star characterization of I star for system parameters or even part, I think it is valid even for part of system parameters.
Yeah, it is. So I think I hope it's valid in a slightly more generality than what I wrote, but writing that statement will take a lot of time. So I just only wrote a special case. All that you need is at maximal ideals, it satisfies this property.
Yeah.
Okay, so it's slightly more general than what I wrote, but writing that statement would take a lot of space and also parsing it. So I decided just to shorten it like this.
Yeah, there are some papers by Haberbach where he talks about phantom
So
dimension and phantom resolutions, and so I thought there was some analog of this for those ideals. So those ideals are not necessarily generated by system parameters.
Yeah, I think so. I don't know those results,
Yeah.
that paper very well. So yeah.
Which ideas?
I think ideals of phantom projective dimension or something. There is a class of ideals which are general, which are strictly bigger than this class that is described in Karen Smith's paper, where the same conclusion will hold.
Okay.
I don't know the result.
Right. So that might give other ideals which satisfy this property. I guess that paper and this appeared almost same time.
Okay. Yeah.
And this Hochster's result, theorem 11.1. So
yeah.
he proved that if there exists some balanced Cohen-Macaulay algebra S such that X is in IS, then X is in I star.
Correct.
So, so did he give any concrete example of S? Like
no, I think it has to be constructed in some sequence. I don't know if there is. I did not look very concrete when I read it. Maybe it's.
So it's existential proof that.
Yeah, I would think. I don't know. I don't know if it can be generated in finitely. It's a finite type algebra. I didn't read the proof that carefully in that.
So if you, I'm just asking a sort of a wild question that came to my mind. If you have a system of parameter and then you take some kind of transformation, definitely not invertible. Is there a way to find the, this tight closure for that that ideal, like ideal generated by some transformation?
So it's some ring map that you're.
You're taking a linear, but not necessarily invertible.
No. What do you mean by linear? Where are the coefficients coming from? Linear over what?
From the base ring.
No, but if you are, but not necessarily. But it may not remain a system of parameters. It may not remain n primary.
No, it may not. It may not.
But I say I don't know. I don't know. Sorry. Yeah.
Automorphism of base ring, will it not induce an automorphism of their plus closures?
No, sorry. I thought you meant when you said base ring, you meant the field inside. No, sorry. Then maybe I misunderstood this question. I thought you were saying given an R and you change the ideal by some K linear map where R contains K.
Yeah,
that's what you're saying. I thought that's what you said.
Huh? Yeah, that will be definitely the first case to check.
Yeah, I don't know. I don't know the answer. Because if you, not every K linear map from the system ideal generated by system of parameters to an ideal of R need be it could even be non-primary. Then I don't know what.
Yeah. But suppose it remains M primary, but it may not be a system of parameters. If it is a system of parameters.
If it is M primary, it would be a system of parameters.
Oh yeah. Okay.
Yeah. Right. So I don't know because you're only asking for K linearity. It might just be very difficult to describe even the ideal. How the ideal is transformed. One would only describe how the generators are transformed.
Yeah, so if you take Frobenius power, it remains a system parameter, so the theorem will also apply to that.
Actually, the way to state it, it would prove any system of parameters that is sort of. It doesn't even have to be Frobenius power, because all that is being done is to interpret through a map like this. What does Z for an element Z of R? What does it mean to say it belongs to I star? And independently, what does it mean to say it belongs to IR plus? You interpret that through this map. So it doesn't actually do. All that you need is it doesn't even have to be Frobenius. It could just be anything.
Yeah. So, I mean, for certain ideals, you probably don't require moving to whole of R plus, right? Because you have finitely many elements and the tight closure.
Yeah, sorry.
That is, to get I star, do we need to go to R plus? Won't there be a finite R module?
I don't know the answer. I mean, it is true. It is true that I star is finitely generated, so you only need to check against those for those elements. But we don't know what those elements are, so I don't know how to. Right. So, I mean, once you know that, we just have to check for these finitely many elements. I suppose it can be done in some finite extension, but I don't know the.
So left hand side is always contained in right hand side.
Left hand side is contained in the right.
So
right side,
for
yeah.
the right hand side to be contained left hand side, we know beforehand that I star is finitely generated. So those elements will live inside some finite extension of R.
Yeah. So I think it will happen in some finite extension. But what finite extension? How far do we have to go? Those things I don't know if they are known. I am not aware of that.
Yeah. So the condition says for all large Q.
Condition.
For element to be in I star, the
we are considering domains, so it has to happen for every element. But what I'm saying is how big a module finite extension of R one has to take. I mean, what is the degree of for example, quantified by the degree of the fraction field extension? How big does one have to go to be sure that all potential elements of I star have now been taken care of? That I don't know.
Okay, I think there is one more question. That is fine. That is fine. So I think we don't see any further question. So thanks Manoj for your nice talk. And we shall continue on Friday at the same time.
Yeah. Thank you.
Thank you everyone.